Okay, class, welcome to lecture two. We've talked about the Big Bang. Now we're moving on to the expanding universe and evidence that it is expanding. I might need the glasses for this. Probably not. We shall see. Okay, so the first bit of evidence the um, that the universe is expanding, right? And it was at one point a radiation dominated universe that eventually cooled out and formed matter is the cosmic background radiation. And I'll put some images up into the classroom, right? But the cosmic background radiation, there's a glow, right? There's this faint glow that's cooled over billions of years, and that faint glow it belongs in like the microwave spectrum, so it's very long wavelength, low energy, right? But there's this faint glow that remains behind, right? So in the deepest space, right, in between everything, there is energy. Right? So as the universe expanded, remember, it didn't expand from a single point outwards. The entire thing just grew and grew and grew. Right? It was all the primeval fireball, and then it expanded and expanded and expanded. And as it expanded and expanded, that radiation cooled, matter froze out, but there's still a background radiation, left over. I don't know if the mouse is going to show up, but you can see these links here. Right? I posted them, but please make sure you watch them. Okay, can I move this? Yes, I can. Okay, still experimenting with the tech to get it right. So, the Big Bang happened. There's the cosmic background radiation. Okay, the next big thing is, like we already mentioned, the red shifting of light. Okay, objects that are moving away from us are red shifted. Objects moving towards us are blue shifted because of the Doppler effect. Sorry, I'm just opening a page here in another window. Why is it making me sign in again? Okay. This image here is showing the electromagnetic spectrum. You should have seen that in grade 10. Open up here. Okay, so light is a wave. It's also known as a particle. The particles are photons, but they're traveling in waves. Radio waves and all the way up to gamma rays, they all belong to light or radiation, but we can't see them. All we can see is this small bit, the visible light. Right? So it being a wave, low wave, long wavelength, low energy are radio waves. Higher energy, shorter wavelength are the gamma rays. So light travels in a wave. Okay. And next slide. Oh, come on. So light travels in waves, and according to the Doppler effect, and sound is a wave as well, right? The Doppler effect, if you watch those videos I posted on Thursday before the PD day, light travels in a wave, sound travels in a wave. So if you've ever heard like an ambulance coming closer to you and you hear the pitch of the sound of the siren, and then as the ambulance passes your car and moves away, the pitch changes, it becomes deeper. So if we had a car with a siren standing still, the pitch all around the car would be the same. But as it's moving towards you, you can see that the waves get compressed to a higher frequency, a higher pitch. If it was light, right, those light waves get compressed to a higher frequency, which would be blue light. Right? It may not necessarily look blue, but it's been shifted towards the blue end of the spectrum that is higher energy. If the car is moving away from you, the siren's going to take on a deeper pitch. Or if you have a light source, a galaxy, a distant galaxy moving away from you, the light waves are going to be stretched out. As they are stretched out, they change color. Right? Longer wavelengths correspond to a red light. And so let's hop back to the previous slide. Right? You can see in visible light, the blue materials are at the higher energy or shorter wavelength, and red is at the lower energy or longer wavelength. So if light is moving towards you, it gets compressed into the blue end. If it's moving away from you, it gets decompressed into the red end. So the Doppler effect is key to our understanding. Right? And Hubble, looking out into space, right, what he saw was that the vast majority of galaxies, the light is all shifted into the red end of the spectrum, indicating that the galaxies are moving away from us, indicating an expanding universe. Okay, so how did you see that? By looking at light, how can you tell? Okay, so light comes off in the visible spectrum. Here's the spectrum of light. All these colors combine to make white light. When you heat an element, if I was to heat a pure element, because it has different orbits of electrons, it gives off specific bands of light. This is the emission spectra of an element. Okay? So heated elements emit specific light energies. So if the light from that heated element is passing through a cooler gas, say in the atmosphere of a star, or it's passing through a cooler gas, in a nebula, right? Those energies get absorbed by the cooler gas, and they create the absorption spectrum where we get these lines that are missing from the continuous spectrum. In the lab setting on Earth, we know what each element should look like, what its emission spectrum should be. Right? We know what its absorption spectrum should be. Sorry, the announcements are going.
Connor Gunn, please come to the office. Connor Gunn.
We know what the absorption spectrum should be. Okay? So for each predicted element, we know what the spectrum should look like. But when we look out into deep space, when we analyze the light through spectroscopy, so we'd use a spectroscope, excuse me, to analyze the light, we see that the light is shifted. So if the lines are shifted from where they should be for specific elements, we can determine a red shift or a blue shift. So this diagram here should help illustrate that. If we have a star, actually forget this option, let's look in the middle. This is the control. This is what the absorption spectrum, right, for a specific element would look like on Earth. Okay? If we're looking at the stars and we can see this absorption spectrum, right, we know that this element is in there. We see the same pattern, but if we look, this bold line here is shifted to the red side. This double paired line in the green is shifted into the yellow, right? This group here is shifted this way. Okay? So if the lines are shifted to the red side, that stellar object is moving away from us. If we look here, right, this star that is moving towards us, we look at the spectrum, we look at the central grouping of 3 here, we can see it's shifted into the blue. This line shifted more into the blue. This line shifted into the violet. Okay, this is a blue shift, right? Meaning that this stellar object is moving towards us. So by looking at the light and looking at the amount of shift, we can tell direction, Okay, which way is the object moving, and we can get relative speeds, right, at of their movement. Just going to hit pause here and get a drink. 1 second, please. Okay, so what did Hubble observe, right, in Hubble's law? Right? So this is important. You should be writing this down. You should be putting, let's move this over here. You should be putting stars by this, right? Objects in deep space found to have a redshift. Right? So this is interpreted as that objects in space are moving away from the Earth and that the universe is expanding. The second point, the velocity of various galaxies receding from the Earth is approximately proportional to their distance from the Earth. So in common language, what is this meaning? Right? Is that the more distant the galaxy is, the faster its velocity is away from the planet. So galaxies closer to us are moving away, but more slowly. Galaxies that are very far away from us are still moving away at a much faster pace. Okay? So the majority of the universe that we can see is moving away from the planet. The further away it is from the Earth, the faster it's moving. Okay? There are a few exceptions to this rule. Okay. Some galaxies are moving towards us. For example, Andromeda is moving towards us, and scientists have predicted that in several billions of years, the Milky Way and Andromeda will collide into each other. Let me see how this pen works. Let me try it here. Will it work? Oh, no, that won't work. Okay, continuing on. So this image here is showing the cosmic background radiation. Let's pull this up. So, based on telescopes on the planet and those in our atmosphere and those in outer space, they're looking out into outer space. Right? There's this glow. Right? The reddest spots being the hottest, the deep blue black being the coolest, but there is this non uniform radiation throughout our visible universe. This is the cosmic background radiation. This is what I mentioned before, some of that evidence. Okay, I gotta find a different way to do this. Yeah, let's go to view, zoom. We're at 100%. Let's try 90. Okay, better. And how'd that zoom? I didn't want that to happen. So when we talk about the expanding universe, there are two predicted outcomes. One, the universe continues to expand forever. And as it keeps expanding, it will keep cooling. And eventually the universe will freeze out and be all the energy, all the radiation will be gone, and it will just be a dead, cold universe. The other idea is that the universal expansion will eventually stop. It'll expand to a certain point, and gravity of all the matter will slowly eventually pull the universe over billions and billions and billions of years together back into a primeval fireball again and begin the big we call that the big crunch, and begin the whole universe over again, followed by a big bang, expansion, then collapse, and then expansion, then collapse, and boom, 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 boom. Those are the two possible thoughts. Crucial to all of them is that matter has gravity. All the matter has gravity. Single atom of hydrogen has gravity. You have gravity. Everything has gravity. The more massive an object is, the more gravity it has. So, a high density universe, one with a lot of mass, will eventually contract and go through the big crunch, whereas a low density universe will expand forever. So those are the two theories. Is the universe high density? It will, all the matter will eventually pull back and collapse the universe over billions and billions and billions of years. Or if there's not a lot of matter in the universe will continue to expand forever. Then we get the concept of critical density. The point where gravity acting alone will be just sufficient enough to halt the expansion of the universe. Okay. At critical density, that's the point where the universe will stop expanding. If there's this much matter in the universe, the critical density, the universe will stop expanding. Okay. So we're looking at 5 hydrogen atoms per cubic meter of space. So that's a tiny amount of matter. If the density of the universe exceeds what we calculated to be critical density, expansion will halt. We'll have the big crunch, and all the galaxies will come towards us. The universe will, collapse and crunch and form the primeval fireball, and then the universe is annihilated, and it will all, hopefully restart again. But we'd be long gone. If the density of the universe is below the critical density, and again, the critical density is the point where expansion is supposed to stop, where gravity is strong enough to just halt expansion, right? The universe will continue to expand forever. Right? Just keep on going and going and going. The amount of radiation weakening over distances, the universe getting colder and colder and colder, and there'll be no stars forming. There'll be no new planets. It'll all just stop. Move this. So, with that expanding universe where we're below the critical density, eventually we won't be able to see anything. Everything will just keep moving away. No galaxies will be visible from the planet. All the local stars in the Milky Way, right, they will fade and die and disappear and cool as they run out of hydrogen fuel. And we'll have the cold death of the universe. Right? Long time away, though. So those are the two theories. Right? Expansion, if we're below the critical density, or contraction, right? The collapse of the universe if we're above that critical density. And based on the density of the universe, space-time, right, the plane of our reality will curve in 3 possible ways. This stuff I'm not too worried about. I don't really need you to be concerned about it. It is interesting, but don't stress yourself about the part on the shape of the universe. So if the critical density is above the critical value, so if the density is above the point, um, it's above the point where the universe is stable and the universe would collapse. Space-time is expected to curve back on itself and form a sphere. We call that the closed universe. Right? If the density is at the critical value, the universe will be a flat plane. It will be infinite. And the third option, if the density is below critical value, an expanding universe, the universe will form a negative curvature and it will be infinite. So these images here, closed universe, right? When we'd have the big crunch, right? This is the place where that will happen. right? If the critical value, if the density is at the critical value, we'd be living on a flat plane. No, sorry, this is a universal expansion. This is the critical value one. Sorry, got that backwards. Okay, this is the critical value one, right, where the universe there's no real contraction, no real expansion, and this is where the universe is continuing to expand forever. We think it would form that saddleback, but I wouldn't even worry about this. Just interesting, but it is not important for our level of study. Okay, when we talk about the universe and matter, there's matter in the universe that there's things we still don't understand, right? Concepts of dark energy, concepts of dark matter. In terms of matter, most of the universe is dark matter. Okay? Dark matter is okay. We can't see it, we can't detect it, but there is evidence that it is there. There's evidence that it's exerting gravity and affecting how our universe behaves. So there's something out there, right? There's also dark energy. Right? There are these parameters we don't understand, and we're doing our best to explain them. And one of our best ways of explaining it is the existence of dark matter. So our knowledge is not complete of the universe and how it operates. So dark matter. Most of the matter in the universe is dark matter. It does not react with radiation the way that matter does. So it doesn't reflect light. It doesn't absorb light and become hot, right? Like, think about you lying out on the beach and the sun's hitting you and your body gets hot, right? You're absorbing energy. You can either absorb energy, you can either reflect energy like a piece of glass reflecting light, or the energy can pass through you. Dark matter does not react with light in the same way. It does not react with radiation in the same way. The only way we know dark matter exists, looks like I spelt that wrong, is there's evidence that there's something there because of the way galaxies are forming and the way they're clustering together. There's evidence that there's these strong gravitational, we call them the great attractor. And in our galaxy group, there's this thing called the great attractor. We don't know what it is, but in our local group, some of the galaxies are moving together. Most of the galaxies are moving away, but in our local group, in our local neighborhood of the universe, some of the galaxies are being pulled together. We think that's dark matter. So, what we think we have, right? And again, this isn't important. I'm not testing you on this. It's just interesting. Including dark matter and dark energy, right? We think that our density parameter is near 1. So we're in a critical universe, but it's expanding. Okay. The other thing that scientists have determined is that this universal expansion is increasing. Okay. So there's a type of stellar phenomenon known as a supernova, and more specifically a type 1 supernova. When type 1 supernovas occur, and this should have been in the video you watched, type 1 supernovas all have a constant brightness or constant luminosity. So that gives us a thing to measure. We can look out in distant galaxies and we can see type 1 supernovas occurring. Right? They all should have the same brightness based on, or they should all be emitting the relatively same amount of energy. Based on how bright they appear to us at Earth, we can predict how far away those objects are. Okay? So with all this information, and we'll be explaining more about that later, what they've determined, and this is important, is that the universal expansion is accelerating. Okay? So universal expansion is accelerating. I want you to write that down. The universe is getting bigger and bigger, faster and faster. This next point here is not going to make a ton of sense. We're going to have to think about it. Nearer supernovas, right? Stars that go supernova closer to us are more redshifted versus supernovas that are further away from us. They're less redshifted. So, how does that statement indicate that the universe is accelerating faster and faster? So I'm just going to try and make a sketch here, okay, to help us understand. I don't know if it's going to work. Okay, there's us in the center of this piece of paper. It's kind of hard to align. Now, remember that light from far away So I'm going to mark two supernovas here. There's supernova 1, far away, and number 2, close. So I don't know if you can see it. I hope you can. And let's get a little closer. I can't see because I'm blocking the camera with the paper. Okay. So if we have an object that is close to us, and we see it, its light is newer than a distant object. The further away the supernova is, the older it is. Okay, the older that light. So if we see a supernova today that is 100 million light years away, right, it took that light 100 million years to reach us. A supernova 4 light years away, it only took that light 4 years to reach us. Right? So, again, going back to this, right, the object far away, its light is older and it is less redshifted. The object closer to us, right, is more redshifted. Right? So the redshift is less for old light, newer light is more redshifted. So old light has small amounts of redshift, newer light has larger amounts of redshift. So new light is moving faster than old light. Okay, light that was emitted 4 years ago is moving faster than light that was emitted from a distant galaxy, 100 million years ago. So what this means is that the newer light has more redshift. That means it's moving away from us faster than the older light. So the older light was moving away slowly. The newer light is moving away much more rapidly. What was that? Okay, so people are morons. I mean, like, really morons. So what that means is that the universe was expanding 100 million years ago, still expanding now, but it's expanding way, way faster. It's accelerating. Its expansion is getting faster and faster and faster. That's a critical point. Let me zoom out of here a little bit. View, zoom. Nope, that's not enough. Zoom. Let's go 80%. Frustrating. Zoom. So this is helping us illustrate Hubble's law. Okay. Here we have redshift, the amount that light is shifted, and we've got distance, right? How far away the object is. Man, let's get a little closer. It will help. This is kind of complicated. Let's try zoom 80%. Oop. Okay, so this black line, right? The black line represents what we call the constant, right? So if the universal expansion was constant, right, distance and redshift would be in proportion. We'd have a straight, red line. Sorry, straight black line. Below the black line, though, is where we see most of the distant galaxies. The distant galaxies are not fitting on the straight line we would expect. Most of the distant galaxies are below. So ancient light from these galaxies is less redshifted than we initially predicted. Okay, so the data is showing that most of the old galaxies, their light, let me rephrase that. Most of the very far away galaxies, their light is not on the constant we observe. Right? We generally observe Hubble's constant. The amount of redshift in the distance was in a straight line, right? The line of best fit, it was all straight. But then we see that from that black line, a lot of these galaxies are below that line. So they're not moving at the rate we expected. So distant ancient light from these galaxies is less redshifted than new light from nearby galaxies. Therefore, the galaxy was expanding more slowly in the past and is expanding faster now. Okay, key point. Make sure you write that down. Excuse me. So, what is causing this expansion? Where is it coming from? What is forcing the universe to expand out quicker and quicker and quicker? What's driving the Big Bang still? One of the theories is dark energy. Okay. This is a guess almost. Well, I wouldn't say a guess, that's being too simplistic. Oh, excuse me. So, dark energy, very theoretical. In dark energy, we really don't know what it is. It's not matter, it's not radiation. But what's thought about dark energy is that it has a repulsive effect on the universe. So it's speeding up the matter and the radiation and everything inside the universe. It is speeding up acceleration, and the effect of its repulsion of pushing the universe outwards increases with how big the universe is. So as the universe gets bigger, the repulsion increases, speeding up expansion. Again, the scientists are guessing. We don't know. We don't know why the universe is expanding faster and faster and faster, but it is. And our best scientists, right, their predictions, 5% of the total mass of the universe is normal matter, luminous matter. That includes you and the air you breathe, right? And your classmates and your desk and whatever, your clothes on your body. That's all normal matter. Okay? They say 25% of the matter in the universe is dark matter. Right? And dark matter we can't see. It doesn't interact with energy the way we know other matter does. We just have data that indicates it has some gravitational effect and that it's out there, but we can't see it or interact with it. And then we've got dark energy, which we think is 70% of the total mass of the universe, and we don't know what that does. Right? We just don't know. Okay, now I'm going to click on this, and we'll see if it'll work. Control, click to follow link.
The universe is expanding.
I don't know
you
if
zoom
you
out
can
far
see
enough,
that.
you'll find that everywhere in the universe is moving away from everything.
Anyways, you can watch that one on your own. I've posted it. I'm going to add this to the YouTube channel, and we'll see how this works.